Hello everyone. Today I'm gonna to introduce our binding project, the Hong Kong Nanchang 220 Transitional Housing Project. Let's begin with the background of the project. Hong Kong's housing crisis by the late 2010s, public housing waiting times topped 5 years, and the low-income families in Shan Shui Po suffered from overcrowded, unsafe subdivided units. So the Hong Kong government turned to transitional housing, also called TH, as a quick fix, boosting funding to 5 billion Hong Kong dollars and targeting 15,000 TH units by 2020. So the Nanchang 220 was a pioneer. Hong Kong's first steel structure TH using MIC tech is set in Shan Shui Po's Nanchang Street, an area with severe housing stress, and it aimed at two goals. The first one is help families waiting greater than 3 years for public housing, and it tests fast, sustainable building for urban temporary land. And the key collaboration is public, private, and community. So the line is donated by Henderson Line, and it has the funding from Community Care Fund for 37.69 million. And this project starts 4-story building finished in July 2020 and 89 units, and it can house 175 people for 2 years. So this project has its own innovations. It has shared economy, for example, the Nanchang Sharing Center for borrow tools or items, and the MIC modules reused later. So why it matters? I think because it is set a benchmark for Hong Kong's transitional housing and proving MIC speed and multi-stakeholder collaboration works. So let's go through with the work breakdown structure. Our project is located at Nanchang Street, Shan Shui Po. The main goal is to build a 4-story steel structure building with 89 units, all using MIC technology, which means 68 module units prefabricated in factories. We need to finish assembly within 12 months, pass all government inspections, and house 162 residents for 2 years, and then dismantle the modules for 100% reuse. And the key constraints are temporary land permits, coordination between MIC prefabrication and on-site hoisting, the Hong Kong street environmental rules and full recycling requirements. And the work breakdown structure that I designed, it covered the entire project lifecycle with 7 level 1 activities, 16 level 2 core tasks, and 33 level 3 subtasks. Each low-level task takes 3 to 14 days, making progress is very easy to track. So I will walk through the work breakdown structure of our project. And first, project initiation and preliminary preparation. We will compile basic documents like the project charter and the feasibility study, then apply for compliance, including a 2-year temporary land permit. We will also collaborate with Henderson Land for the land, build our core team with MIC experts, and secure 37.69 million Hong Kong dollars in funding. Plus, we will engage the local community, hold residents meetings, and survey potential residents' needs for 1 to 3% units. And then next, design an MIC module prefabrication. We will finalize the 4-story layout with 89 units and split the building into 68 standardized MIC modules. So after internal technical reviews and government approval from the buildings department, we will start factory prefabrication and like procuring steel, producing modules, pre-installing water, electricity, kitchens, and furniture, then conducting strict quality inspections before delivery. So third, on-site assembly and main construction. We will level the site, erect enclosures, and deploy cranes. For the foundation, we will go geological surveys, pour concrete, and install embedded parts, all inspected by supervisors. Then comes the key MIC assembly. Transport modules in 10 batches, splice floor by floor, 4 days per floor, 16 days total, and then reinforce connection and finish the exterior. Throughout, we will control dust and noise with 4 canals and sound barriers, and conduct daily safety tests. And fourth, supporting facilities, we will connect to municipal water, electricity, and gas, test all pipelines, build public spaces like activity rooms and children's play areas, install access control and firefighting systems, then clean and configure each unit with appliances before minor repairs. So finally, quality inspection and compliance. We will test the module splicing strength, structural safety, and indoor air quality, then pass specialized inspection from the buildings department, fire services department, and environmental protection department. Any defects will be rectified quickly, and all documents will be filed with the government. So to sign up, our WBS is streamlined but comprehensive, focusing on MIC efficiency, multi-stakeholder collaboration, and Hong Kong's compliance requirements. It ensures every phase is manageable, trackable, and aligned with the project's goals of speed, sustainability, and community impact. So that's my work breakdown structure overview. Thank you for listening. Let's move to next section.
Let me to discuss the detailed schedule of this construction project. The durations of this project is around 330 days without the preparation works like the community engagements or the design issue, which may increase around 45 days. For this project, most of the schedule is similar to other projects, so that I will not spend much time on discussing these schedules. One special thing I need to point out is that you can see we defined Zoom A and Zoom B in the program, and there are a little bit difference that Zoom A requires 7 days per each level for constructing ground level to the flag level. However, Zoom B can make 4-day cycles per each floor in the construction period. The reason is MIC method is still new technology in Hong Kong construction industry. The worker and the supervision team have to learn is there any difficulties on installing the MIC model. Let's say you can show how grades of the steel frame, and the supervisor can point out some improvements works of the installations of the MIC module. So you can see that Sumi is just around 10% of the MIC models. It can just learn the connections of the verticals and horizontals between each MIC models. Then, that is the networks for this project. It shows that most of the tasks are in the critical path. Their only mock-up is not on the critical path, which is item D. The reason is the mock-up can be done more earlier for the clients to review in the precast factory, but it must be complete before the mass production. So it will not affect the site operation before the installation works of the MIC module. And finally, this is the contracts of this project.
Okay, next I will talk about the cost estimation section of our project. This analysis provides the com comprehensive breakdown of all project costs with both normal and crash time. Our cost estimation followed the detailed WBS structure from our project and completes with Hong Kong Institute of Surveys guidelines. We use the current market rates and all costs expressed in Hong Kong dollars. For every activities, we conduct timed cost trade-off analysis to determine both normal and crash parameters. Importantly, even in the crash time, we maintain all the technical quality and safety standards. Our analysis shows the project can be completed in 45 days plus 330 days under normal conditions, or compressed to 32 days plus 254 days in crash time. Key compression opportunities exist in item 8, project preparation works, which can be reduced from 45 to 32 days. And the project C, design submission process, which can be shortened from 98 to 72 days. The item G, frame of the superstructured activity, offers to most significant compressions potential, reducing from the 79 day to 63 days. This is the detailed cost breakdown by activity. Item I, the OP applications process requires special attention. Each submission item needs exactly 1 date for government processing and cannot be accelerated regardless of additional resources. Therefore, no crash time or crash cost options are available for this activity. Our indirect cost showed a significant increase in crash time. Project management cost raised by 20%, while equipment rentals and maintenance cost increased by 31.5%, reflecting the primates for expedite equipment access during the accelerated work. The total project cost distribution shows the direct cost accounts for 62.3% of the budget, with indirect cost at 21.4% and contingencies at 11.5%. Under normal conditions, the total project cost in 86.35 million Hong Kong dollars, while the crash time totals 108.47 million Hong Kong dollars. Both figures remained well within the 100 and 120 to 150 million Hong Kong dollars budget when specified in the standard requirements. That's all.
Hello everyone, my name is Zhang Deyao. This is my part, project control. There are 4 parts: schedule control, cost control, quality control, and risk control. First, schedule control. We set a clear baseline, 316 days from August 1st, 2019 to July 5th, 2020, covering 4 keynotes: set establishment, design approval, superstructure frame, and finishing works. Task dependencies are clearly defined, such as MIC component design starting post-footing completion. 3-level monitoring mechanism is in place: daily progress recording, weekly progress reviews, and monthly deviation visualization. For deviations, minor ones are fixed by overtime or actual workers. Major ones by adjusting non-critical tasks. Next, cost control. The budget is Hong Kong dollar 120 to 150 million, accounting for 50% of the company's annual turnover. We allocated cost to each task and reserved 5% to 8% contingency funds for geological anomalies. We adopt earned value management to track PV, AC, and EV, using CV and SV for oversight. Cost optimization includes bulk procurement and supplier binding for materials like MSC components, modular construction with advanced equipment, and reuse of excavated soil to cut waste cost. Then, quality control. Our project's lifeline, we built a full cycle system: pre-construction design reviews, material sampling test, and certified staff training. In construction, stop checkpoints, standardized workflows, and a 21-day mock-up post-construction single-item acceptance, documents submissions, and final occupation permit application. Finally, risk control. We identified 4 risk categories: schedule risk, cost risks, quality risks, and compliance risks. And the risk assignment: high-risk design approval delay, geological change, component quality issues; and the medium risk: material price fluctuation, bad weather, substandard pipe work; and the low risk: minor document submission delay, slight material waste. And the response measures: high risk, we should dedicated staff track approval and backup designs, detailed geological survey, and reserve materials. And the medium risk and low risk here is risk monitoring, regular review, update risk register in weekly meetings or monthly reports, and emergency plans, established multiple supplier partnerships for critical risk. Then we will carry out the optimization analysis of project progress. First of all, the previous students have drawn the activity on node diagram, and some students have also calculated the cost. We need to conduct analysis and optimization on this basis, and we will use Lingo software for this purpose. First, we need to define the decision variables. Let xi equal earliest finish time for activity I, and yi equals the amount the activity I is crashed. Note that we should we should know that the program I cannot be crashed. Yes. Then input these constraints into Lingo. Yes, it's here. These are the data analyzed through Lingo. As we can see, the crash time for all current activities is 0, and the earliest finish time for each activity has also been determined. Ultimately, the project can be completed within 302 days, which meets the schedule optimization target. Yes, that's all.